Hey there, everybody! Welcome back to your second installment of Chem Phys Full-Length 4 Review. You might have noticed I'm not Kristen. It's true. I like to pretend that I'm Kristen. Sometimes I act like I'm Kristen, but I'm not. She had a bit of a medical issue, and so she's actually stepping out for the evening. I know, right? People thought I might be Kristen, but I'm not. So basically, Dom stepped in for the previous class. I'm stepping in for this one. As you know, we like to be a team as much as possible. When someone's injured, we do what we can. Apparently, she would only be able to teach like this. It's a neck injury, and it's kind of hard to teach with your head pointing straight down. So hopefully we'll have fun regardless. So welcome, my name's John Lennick. I'll be your host and tour guide, stepping in for Kristen for today. Thanks, Caitlin. We appreciate it. We do what we can. We do what we can. What we'll do today, I just want to set the tone at the very beginning. I know we do have most people that were here for the previous session. We got a couple newbies joining the group as well. You need to have taken full-length 4 in order to be in this class. If you haven't taken it yet, don't be here, log out, come back later on after you've taken it. These are all recorded. You could just jump in and watch a recording anytime you want. What's going on, Fong? Bunch of familiar names. Good to see you. And so let us know if you have any questions. Of course, it's not just me, of course. It is also, yeah, actually, Dom, are you hanging out too for this one? I'm not sure if Dom's hanging out for this one. But of course, also, Paul's going to be here as before, so Dom and Paul are both here. If you have any questions, please hit us up. We can, of course, answer any questions that you have in the chat. And my pen tool is not working. I apologize. There it goes. Okay, sorry about that little delay there. All right, so what we'll do, of course, today we're going to run through a couple different learning goals. Remember, this is not meant to be a comprehensive review of your entire full length. Instead, we actually picked a couple individual questions to cover a couple of very common themes that you'll see in the test. First things first, as you know, figures, graphs, tables, units, stuff like that, in both the question stems and the answer choices. So we picked a bunch of the ones from full-length 4 Chem Phys to use as an example of how to really do some figure and unit analysis and how to solve things more quickly and efficiently than might seem really noticeable on first glance. After that, we'll go through answer choices that have very repetitive structure, increase, increase, decrease, decrease. And basically go through a couple of those and show how you can save yourself a bunch of time by eliminating a couple and then choosing between the two left over, or of course narrowing it down to one answer fairly quickly. So today's class is really all about efficiency and running through general strategies that don't just apply to full-length 4, but it apply to all of your full-length exams and practice tests and quizzes because we do see lots of questions that follow these same major formats. All right, perfect. Yeah, I like this one. I'm a big fan of this class especially. So let's go through question number 8 first and foremost. We'll try to make this where it's fairly independent, of course, of the passage. And if you do need a passage, we're going to pull it out for you. So first things first, do we need the passage to solve this one? One thing you do need to know. Actually, I would say you do need something from the passage. There's actually 2 things I'd say you need. Well, maybe not. Actually, if you guys are really good at this and you understand how springs work, the one thing is that we do have, I'm going to go with you guys. Let's just say no straight up, because it's true, you could solve this out your background knowledge of this thing here. Do you guys remember how this was like I forgot what we called it. It was like it was the Voigt model. It was a, physioelastic material. I forgot the name of it. It was a stretchy thing. Basically, it was the stretchy thing, and then also we have springs. Exactly, we have that equation. There we go. And so now here's kind of the cool thing as well. What do we know about springs, though, when you apply a force to a spring? What's going to eventually happen? I like that you guys said no, because I just realized we could probably solve this without even using the passage at all. What's going to happen to a displacement as you pull on a spring? Eventually. Yeah, eventually it's going to, well, if you let go of it, it'll collapse and it'll come back to equilibrium. But if you have a spring attached to a wall, you grab it, you start to pull, eventually what's going to happen as you pull harder, 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 eventually it's just going to max out. It's not going to go any further. Like, you can't stretch it out for infinitely. Eventually you'd pretty much straighten it out all the way, and then it would just be right there, and it stops. It's not going to move any further. So actually, that alone can pretty much answer this question for us because you know that it's going to basically flatten out where displacement will level off over time. Now, the main reason why that we know that, though, is because 2 things. Well, actually, we'll go through the full passage. I'll show you how this works. But you guys are totally right. You could have solved this without even using the passage. But I would say there's two things to make this easier. The Maxwell model, exactly as Charmaine's saying, as well as the Voigt model that we have as well. Maxwell model shows that elastic springs basically deform instantaneously. And the Voigt model talked about, of course, this asymptotic, if that's a word, curve, where basically went off. So here we go. Let's look at these two things. So the main idea when we looked at the Maxwell model is that the curve eventually, did it flatten out with the Maxwell model? Did it eventually flatten out? I think you guys remember this from the passage. This is actually a good way to talk about circuits as well. Kind of connects parallel versus series and how we can discuss a couple background concepts. Yeah, it's got a sharp incline, Kaylin, exactly true. Would this be series or parallel? Let's do some circuit talk. We'll try to tie in other concepts as much as possible today. A series model, exactly. So this is a series system. The whole idea is we've got the spring there, and so we said the spring's going to basically stretch instantaneously. It's not going to apply force until you displace it. Because what is Hooke's law? What's your formula for, of course, the force that the spring's going to pull back on you with? Do you guys remember your Hooke's law formula? What the force of a spring is equal to? Important formula here. Shows up surprisingly amount still, even with the test change. So force on a spring is equal to, you guys remember this formula? Close. 1/2 kx squared is actually, that'd be the potential energy of a spring. Force is just negative kx. You got it. So what's x stand for, though? That's the more important thing. That's what we're really going to get into here. Displacement. Displacement from equilibrium, to be really specific about that. And so the whole idea is when the spring's in equilibrium, it's yet to be displaced, it's not going to offer any resistive force. Like it's pretty easy to pull a spring. As soon as you displace it, though, yeah, then the thing's actually going to start to pull back on you. That's exactly true. Whereas this guy right here, this was your elastic material. This was not like Stretch Armstrong. What would be a good example of this? It's something that if you pull on it, it eventually keeps going and keeps going and it keeps going and keeps going. It's more like silly putty. So that eventually basically goes in a straight line. It will keep stretching as far as you pull it. It doesn't really have equilibrium in the same sense that a spring does. So now, what if we put these two in this context, though? What do you call this system of connecting? This is going to connect it to other topics, as we will try to do. It's parallel, right? And so notice when it's parallel, what's going to cause a problem? What's going to stop this thing from stretching out infinitely? Now, what part of it? The spring, exactly true, Marlo, Robert, exactly true. So the whole idea is when you pull this thing, you start to tug on it, yeah, this thing would stretch out infinitely, but since the spring has a maximum displacement, you can't stretch it out forever, it is going to basically bottom out. It will flatten out like that, exactly true. So now what they're doing is making us combine these two different models and see, of course, how it's going to relate to your, the image basically shown in the question stem. And so, of course, when it's in series, there's no limit, whereas we did have a limit when we had them in parallel. So if you look at this system right here, notice there's two different things. We have a system in parallel, which we know is going to have an asymptote, as well as another one in series, but it's not a stretchy thing in series. It's a spring in series, which means what's our best answer here, if we remember from the quiz? You got it. Answer choice C. It's going to be the same as when we had it in parallel. It's going to flatten out. Now, let's play with this, though. What would happen if we instead moved this thing right here? What if we had that? Then what would happen if we made that into an elastic material instead of a spring? Yeah, Robert, if that was the case, then it would be D, because even though this thing is going to max out, it'll hit its maximum, it will limit, this thing here is going to stretch forever. And since it's in series with this entire parallel system, you would get D for that answer choice. So that's the cool thing you want to do when you go through these tests and do your review. It's why we do that stuff in these exam reviews as well. It's not just to be like, oh, the answer's this, or oh, yeah, it says this. Change it around. Be like, all right, well, if we change the question stem to say this instead, how would the answer change? That's the way to really get inside the head of the test maker and figure out not only the ways that they ask questions, but the different types of ways they can ask it. The way that AAMC seemingly does things, we don't really know. They're very secretive. But it's kind of like they have basically a big question pool where they have a bunch of different types of questions, but then they'll edit them. They'll make small changes. They'll switch things around. They'll reorganize passages. There's so many questions that they have. It just makes more sense to do it that way. That's pure conjecture, but it just makes sense. especially because, as you can see, with all of those old AAMC full-length exams that we've analyzed for years in the past, so many questions show up so many times in so many of the exams, just phrased a little bit differently. So if you get used to taking their questions and rewriting them into different formats, it really kind of shows you the way that they're doing it themselves. So that's why we like to do stuff like this. All right, we'll move on to the next one, still sticking with graphs as our learning goal suggests, right here. So first things first, stop, look at the answers. We've got a bunch of Roman numerals here, so we need to rank these different things according to, of course, what? So what is the question really getting at here? There's a couple things you could say here. Two things. Yeah, exactly. Absorbance you got at Marlowe, as well as wavelength, exactly true. So we're comparing wavelength and absorbance. And so before we really get into this, we're talking about sunscreens. So do we want maximum absorbance or minimal absorbance? Since we're talking about potential sunscreens. If you're going to a tanning bed, maybe, but you want max, because the whole idea is if you cover the sunscreen in your skin and that sunscreen's good at absorbing all the sun rays, they can't get through and actually get to your skin. Oh, I see. I think what are you getting, Caitlin? I think you and Alyssa might have been talking about the same thing. We'll get to that in 1 second. So generally speaking, though, we do want maximum absorbance, but I think I know what you meant by that, and we'll talk about that on the very next page right here. So we want strong sunscreen, thus we want a lot of absorbance, I would say. I think you might have been referring to some wavelength stuff there when you said min. Let me know if that was true. Yeah, I had a hunch. I was like, maybe that was a different question, which is totally correct. All right, so before we get into this question, I want to do a little bit of a review here and just talk about the electromagnetic spectrum. You do need to know the relative differences in wavelength, frequency, and energy of the electromagnetic spectrum. So looking here, we've got part of this already basically filled out for you. You've got frequency in top, thus you have maximum frequency for your gamma rays, whereas you have maximum wavelength for the radio waves right there. Specifically, well, here's a question for you. What has a longer wavelength, FM radio waves or AM radio waves? What is a longer wavelength, FM or AM? Nice, it is AM radio waves, exactly true. The way that we can remember this is to, well, first of all, remember our relationship between energy and wavelength and frequency. And so what is that relationship? How do we tie energy in to this whole mix? There's actually a formula which you need to memorize too. Feel free to, yeah, there you go, Marla. So first of all, energy goes with frequency. So if we wanted to actually map this in terms of energy, you would be increasing your energy as you go to the left. And there we go, Marlo. Alyssa's got the same thing. Memorize that equation. E equals hf. That's energy equals Planck's constant times frequency. Do you know Planck's constant? At least the exponent's what you want to know. It's at 1, or not, it's 6.6, but we'll round it to 1. Close. That's your Avogadro's number. It's actually a negative exponent. But it's about 6, I think it's 6.626. We'll just call it 6.6 times 10 to the negative 34th. If you guys didn't know that one. Cool. So that's your Planck's constant. That's just h right there. Honestly, I would say it's a decent one to memorize. This is one of those things that you never really know. In the past, it has been tested, of course, explicitly where you need to memorize it. It's, though, also been given more often than it's been required. So it's one of those things that it depends which teacher you talk to. If someone had it to memorize it on their MCAT, they'll probably tell you to memorize it. If it was given on theirs, they'll probably tell you not to bother. It's literally, it's up in the air. We don't really know which is more likely to occur, and so it's better to be safe than sorry, in my opinion. All right, so energy, of course, increases as you go to the left, as we have going down right there. And so let's jump back to radio waves. So we said AM radio waves is going to be lower energy than FM radio waves. This is actually why AM radio waves travel further. Have you ever noticed that for FM radio, like you can hear it really closely when you're in the city, but once you get out in the middle of nowhere, all you're really picking up is AM? The whole reason why FM radio waves are so strong, they can actually brace through the atmosphere and make it out to space. AM is such a big wavelength, low energy wave that it can't break through the clouds, and so it goes up, hits the clouds, bounces off, comes back down, thus making it actually travel quite a bit further, since FM is just going to basically go up into space and leave. So if you're an alien and you want to check out the planet Earth, you can only really listen to FM radio. So too bad they can't hear our AM, public radio stuff that we do. All right, so jokes aside, as we said, radio waves, we got some wavelength there. We know gamma rays are the highest energy. That's why, of course, gamma rays cause cancer. It's why it can turn you into the Hulk if you're into comic books, exactly, and all of that. The ones that you do need to know, of course, is in the electromagnetic spectrum in terms of visual. So you do want to have this memorized. Know that violet's around 380 or so. That's the highest frequency, right? Most energetic visible light. Red's closer, and red's closer down to like 750 nanometers, thus the lowest energy, lowest frequency, because it's got the highest. All right, there we go. So as we said, energy increases as it goes to the left. And then, of course, you want to know the order, though, right? So if you get a little bit lower energy than visible, it means you're talking infrared. If you're talking about a little bit higher energy, it's UV. That's why when we talk about sunscreen, we need to block out the UV rays, so the stuff that's in the high energy, high frequency, right, thus low wavelength side, is what we really want to be blocking out. So with that in mind, looking back to our passage and actually showing the formulas that we have, we already talked about all that stuff, which two answer choices are going to be the best? What are the strongest in terms of course, absorbance? So we already went through energy, got that covered. Which ones look great? Given that we want to block out, yeah, 4 is the best by far, and then also what other one looks good, given that we want to block out the ultraviolet highest energy light of them all? 1. So no matter what, 1 and 4 are going to be the golden ones. That's what we care about the most, which means if either of them appear too late in the list, we can eliminate it. So we want, of course, as we said, a lowest wavelength, thus highest energy, thus lowest frequency. And notice if you look at A, hey, look, A, 1 appears last. Look at B, oh, hey, 1 appears last. Looking at C, 4 again appears last. You don't even have to actually rank these. Only one possible answer shows number 1 and number 4 being basically in the better side, the stronger, basically the stronger absorption, thus the better sunscreen that we have. Cool. Cool. There we go. Sweet. I think that just got cleared up. All right. Know your electromagnetic spectrum. Know the borders of visible light. Know the order. Gamma, X-ray, UV, visible, infrared, microwave, radio waves, all the way down. Really important. That stuff does show up quite a bit. It's really big, I'd say, on the AAMC's list of like atomic nuclear type phenomenon stuff that still does get tested quite a bit. All right. So number 30, another great one. So stop, look at the answers. We've got tons of units. Does anyone get a little bit intimidated when we see these questions where it's like, which of the following is not equivalent? Oh my gosh, people hate these. What does that mean, though? Just like conceptually speaking. What does that mean about 3 of the answers, I guess you could say? You got it, Marlo. So this is actually really common where they'll give you 4 different answer choices. 3 are correct derivations of the units. 1's totally different. So now the cool thing is, if we know that 3 of them effectively have the same units and 1's different, we don't actually care about anything in the question stem. All we care about is which of the following is not equivalent to T. Not only that, like, of course, ideally you would then, like, think about your units. You'd be like, okay, well, your formula for magnetic field, you can use F equals QVB sine theta. You can use your formula for magnetic field. That first one was magnetic force. Actually, let me label these real quick. So this one, as we said, is your magnetic force. This one, of course, solves for your magnetic field. But even if you didn't memorize these things, and like ideally, yeah, you could use this. It's a great starting point. You could break down your units, find the right ones. You don't have to. There's an easier way to do this. Since you know 3 are going to be the same and 1's going to be different, let's just play the Sesame Street game of which of these things is not like the other, which is one of my favorite things to play on the MCAT. So since these have a bunch of different units, let's try to identify some of the unique units. Like, for example, if you think about your fundamental units, like force is going to break down into components of seconds, energy is going to break down into components of seconds. All these things do have, like, generally meters, seconds, kilograms are very much your fundamental units, so it's hard to start with those. So let's pick the more unique ones. What are some, like, unique units here that we can really work with? They don't appear as often, I would say, in the question stem. I have a couple I'd pick. What do you guys think? Yeah, let's go with amps in the first one. Newtons I'll leave alone because newtons breaks down to give, seconds and kilograms and all that stuff. Volts, that's another one that's kind of unique. I would go with coulombs too. So instead of dealing with the stuff like the newtons where you have kilograms, meters, seconds, all that kind of stuff, let's just stick with the fundamentals that deal with charge. Because every single answer choice does have something that relates to charge, whether it's amps, that's coulombs per second, volts, that's joules per coulomb. We kind of just focus on the charge thing, and that alone will let us eliminate anything that we don't want. So let's not even touch the seconds, meters, kilograms, any of that stuff. So first things first, we'll look at the actual first one here. So the units of amps is what? What are the units of amps again? We'll go with A first. Coulombs per second, you got it. So there's the ones that we said we were going to talk about. Looking, of course, right there. This one is coulombs per second. So now if we rearrange this, where does coulombs appear to be? In the numerator or the denominator? It's in the denominator. So all we really need to do now is say, okay, for this one, coulombs in the denominator, right? Notice if you look at B, coulombs is also in the denominator. Now, the thing is, you don't even have to bother dealing with C and D, because notice if you look at D directly, you're like, oh, hey, it has coulombs in the numerator. That one is different than the others because both A and B have it in the denominator, so your correct answer has to be D without even looking at C. You guys see what we just did here? We just ninja'd it. If you want to be really fancy, volts is joules per coulomb, and so you can, of course, rewrite that so that also has coulombs in the denominator. You could also look at kilograms. The reason that I didn't want to deal with kilograms, because I agree it's also, if you look at A and D have the same thing, it's just because newtons basically can break down to component units, and voltage also is joules per coulomb, right? And then joules breaks down to newtons meters. And so it just involved a couple more steps, but you could totally do kilogram instead. I just like picking the ones that involve the less derivations, and because if you do kilograms, you have to break everything down into it. You know what I mean? So, does that make sense? We feeling pretty good? How to ninja our way through these? Pretty fun, right? Save you a bunch of time. Cool. So, yeah, as Paul says, completely ninja. That's the way we like to do this. Cool. All right, let's go through a couple other ones here. Looking here, stop and looking at the answers. What do you notice about the answers here? Yeah, a lot of similarities. Once again, you got it. We're not going to do any math. Nice call. We've got some common numbers. Specifically, we've got 2, we've got 1620, and we've also got this 4190. So really what this question is, it's an order of operations question. And so if you guys don't remember your order of operations, please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, and finally subtraction. Nice, perfect, good to hear, Kaylin. And so you got it. So it is actually an order of operations question. The one thing, though, is you also need to relate what we're actually talking about. So if we're talking about changing the temperature of water, given heat capacities, joules, heat, what formula do you need to know here? This is a very important formula. You got it, the MCAT formula. So heat equals MC delta T. Perfect, you guys know it. So that's the first thing I would say. So this is going to be an MCAT question. That's a pun right there, because yes, heat question. Additionally, we got to figure out what the heck these things mean. So what is 1620? is, you got it, it's the heat capacity of the bomb calorimeter. And so then what the heck do you think 4190 is? Because I don't see it in the question stem. Technically speaking, it's in the passage, but I bet you can figure it out otherwise. Given that we're using the MCAT formula, what's that probably dealing with? Bingo, Marlo, that's the specific heat of water. Nice work. And so what's the difference between specific heat and heat capacity? To use a little bit of our background knowledge, as we like to do in these classes, not just go through the question, but tie other stuff together. So what's the difference? Because this is a common misconception. Nice, Emily, good work. So yeah, we tend to use heat capacity is written as a capital C, but all it means is you take the mass times the specific heat. So specific heat, that's actually just a little c, that's a property of the element. So heat capacity just basically includes mass times your specific heat. So nice work, Emily. All right, so then we've also got this 275. I don't really know what that is. That looks kind of random. Maybe it'll show up later. We can figure it out. All right, so as we said, well, I guess since that's random, we can knock it out. But we're using the formula Q equals MC delta heat. And so we're solving for the total heat in joules, right? So that means the heat total is going to be equal to, you could say, the MC delta T of the water. And then what else? How else would we finish this formula? One more part. So you got it, the same thing of the bomb calorimeter. Now I'm going to put MC as one term, they gave it to us, but notice all we're saying is the total heat is of course the heat of the water and the heat of the bomb calorimeter. What is the one number that's going to be the same regardless if it's the water or the bomb calorimeter? The temperature change, exactly, which means we're going to have to multiply both of these terms. We can effectively remove them from both these equations and put delta T on the outside. And what was that delta T on the outside? 2. So, oh, look, it looks like it's got to be answer choice C. So notice we remove the 2 on the outside. You have both the specific heat of the water and the bomb calorimeter in there, which means, of course, it's going to be that answer. So those little order of operations in terms of multiplication, division, and all that kind of fun stuff. And it's just important to do a little review whenever possible. Cool. There we go. And Paul's got a good breakdown of those bomb calorimeters and why we use them in the first place. Cool. And also, the reason that we don't care about the mass of the calorimeter is because it gave you the heat capacity. Heat capacity includes mass. That's specific heat times mass. Emily brought that up in chat a little bit ago, so nice work. All right. Let's go on to the next one. So this is a fun little one to go through. It says an axon can be modeled, of course, as a circuit. Looking here at our answer choices, we got a graph of voltage versus time. So what are the main things we actually need from the question stem here? This will be a fun one. There's a couple animations we made for this question. I guess it's mostly a little quiet. I'll just kind of talk about it for a second. So the main thing we're doing, you can tell it from the units too, we're comparing voltage over time, and not only do we have a resistor, we also have a capacitor. So let's real quick just cover, what do capacitors do? They store charge, exactly. So my favorite example of a capacitor is defibrillator panels, right? So if someone basically goes into cardiac arrest, is it MCI? We call it myocardial infarction. But basically, you've got these panels. You say charging, charging, charging. One plate gets very positive. The other plate gets very negative. You then place the panels between the person's heart, and all the charge goes from one to the other in 1 hot second. The more classic examples and how we use them in circuits, though, is like those disposable cameras. So you click the little charger button, and then you hear the thing, where it's basically just there's a tiny battery storing up charge in a capacitor. When it's fully charged, the little red light turns on, and then when you click the flash bulb, all of that energy stored in the capacitor is released in 1 hot second. They have recently made, nice, I like it, 90s, there we go. They recently actually came up with a new form of microcapacitors that they think capacitors might actually be replacing batteries in the near future in terms of, like, you know, energy crisis type stuff. So there's some cool research just came out if you want to do some Googling. Graphene is the answer, though, in case you know what that is. All right, so with that stuff all stated, the main idea is that they store charge. And so we'll kind of go through this as we basically plug it in. So all we need, of course, is the last sentence. As you close the switch, how is the voltage going to change over time? So here's my question for you. What direction will the current be in this circuit? Let's do some background. What's the direction of current? Nice, Emily's got it. The current will, of course, be counterclockwise because remember, that means this plate right there is positive, that one there is negative, and current shows the direction that positive charges travel. So now we're not going to do this with current, but remember, current shows the direction positive charges travel. Instead, I'm going to do this very realistically. Let's talk about electrons, because in reality it is electrons actually moving. We said capacitors store charge. So the idea is if we trace this as an actual electron, because we're going to have some fun with it, that electron, of course, goes through the wire, through the resistor, and when it gets to the plate of the capacitor right there, what happens to this capacitor plate? Does it become positive or does it become negative? And remember, in reality, current, if you describe it as current, it goes the other way. We're just showing this as the electron movement. It becomes negative. You got it. So it starts to develop a negative charge. And then as this plate gets negative, it effectively scares other negative charges away from this plate, which then completes the current, leaving the other side of it positive, going all the way until, of course, it gets right there. Now, as this starts to build up and get more and more and more and more negative, what happens to the current? Yeah, it eventually levels off. What pretty much happens is that you start to build up a voltage difference. Remember, voltage, of course, is just electric potential. So we have a potential between these two plates. So as we start to build up the potential, as you get more and more and more and more charges here, the current starts to drop. And so notice as the current starts to drop, of course, the change in voltage also starts to drop. When you guys actually already said it, and Charmaine brought it up in the chat, it basically levels off. And so, of course, the difference across the voltage there is going to be similar to what happens in the current. Of course, you build up current, build up voltage, and of course, eventually it levels off. Because remember, your current is your basically charges over time. So, as you get more and more and more charges, eventually you won't be able to get any more as stored on the plate. The way that I like to think about capacitors, capacitors are like parties for charges. It's a place for charges to go and hang out. And if you come to the circuits class, we give you some super cheesy mnemonics. Actually, I'll just give you guys it right now because it's a really good one. I did not invent this. Actually, the summer intensive students, I direct the intensive summer program in Boulder, Colorado. They made this up last summer, but these are the two most common equations that you see for capacitors. And so the fun thing is, remember that we said capacitors are places where charges get to party and hang out. You know what the two good things to bring to parties are? Notice what this looks like up top? See what that is there? Oh, hey, look, it's like a little ice cream cone. Show up to a party with ice cream, people are going to like you. And you know what the other good thing to bring to a party is? That's right, the top of this equation spells the word cake. Cake and ice cream. You got it. You can think of it as a keg stand if you want, Kaylin. That totally works too. It's your call how you want to remember the mnemonic. But those are your two most common capacitor equations. So a little bit cheesy, but the whole point, of course, is to hit a bunch of different content. That's what we're going for now. All right, let us know if you have questions on capacitors. We can get deep, but your circuits class gets really into those quite a bit. All right, a couple more, and the very last learning goal we go through pretty quickly because it's a lot of repetitive structure, but we got about 2 more questions before we do that. This is a good one. This one's very passage-based. This one's pretty tricky. And so do you all remember this was the very last passage in your test? So where we had like the protein isolation stuff. We did like a titration type thing with different acid and chunks, protein chunks. We'll kind of go through the big picture here. But so the main idea here is we're talking about different proteins. We're talking about different anodes and cathodes and how these bands are going to form an electrophoresis. So we've got gel electrophoresis. They separate, of course, things based on size and charge. We primarily do electrophoresis for DNA, and DNA migrates towards what? The anode or the cathode. So if this was DNA, what would it migrate towards? It's a trick question, Kaylin. It's the anode. Emily's right, because notice that the anode actually has a positive charge. What type of cell must this be if the anode has a positive charge? It's tricky. This happens a lot. I know people fall for that every time. We so memorize anodes as negative and cathodes as positive. Anodes are only negative and cathodes are only positive if it's a galvanic cell. This is not spontaneous. You don't use electrophoresis to create energy. It takes energy to run electrophoresis. Excuse me, you got to plug this thing into the wall, which means it's what kind of cell if it's non-spontaneous and you got to plug it into the wall? It means it is an electrolytic cell, exactly. Thus your delta G is what? Positive or negative? Oh, I think it's a mnemonic, Charmaine. I'm not sure what that one is, though. Exactly. It's positive delta G, non-spontaneous. Exactly true. You got it. All right, so non-spontaneous, electrolytic cell. Notice anodes are positive, cathodes are negative for this type of cell. All right, so we need the passage to solve this. We got to actually use data from the passage, most specifically, to actually answer this question. So the passage, this is one, there's actually paragraph 2 gives you a lot more details than this third paragraph right here. But so the whole idea is we're primarily going to use this chart right here. Now what happened in the passage is that we had a bunch of amino acid chunks that were stuck because they basically bound to negative beads inside of this tube. And so what we effectively start doing is we start adding base, adding base, adding base, adding base, adding base. And of course, as soon as you get it to dissociate from the bead, it basically elutes, is what we like to say. So now what that means is that when you add base, we're basically adding negative charges. And when those negative charges bind with the positive charge on your amino acids, because it was starting out very basic, it gets it to basically break off and then go. So when we look at this thing, if it's going to elute at a very low pH, so it didn't take much base, then what do we know about that amino acid chunk or amino acid? If it didn't take a lot of OH to get it to break away from that bead, what would that tell you about the positive charges that it has? So it only took a couple hydroxides to break it off. Would it have a lot of negative charges, positive charges, or little positive charges? Yeah, you gotta remain small, not a lot, right? It only took a couple hydroxides, and it basically knocked that sucker off. So that's effectively what we're doing. These acetate ions bind to the positive charges in the amino acids. Initially, we said that we had this bead that had a negative charge on it, so all the positive charges in your amino acids are stuck to the bead. As you add hydroxides, they basically react to the amino acid and cause them to fall off. So if it's on the far left side of the spectrum, that means that it's not going to have that many positive charges, and as you go up, it gets more and more and more and more positive charges as you go through. Now, even if we were confused with the charges, looking at the order, seeing that it's B, C, E, what 2 answer choices can you eliminate right off the bat? Like, even if you didn't know what was going on in the passage, you can glance at this diagram and eliminate 2 of them. And that's what we want to keep in mind on test day, because this is some complex stuff going on in this passage. You got it. Can't be C, can't be D, because the order's wrong. Notice how it's got the order out. It's going to either be B, D, then E, or E, then D, then B. And so now we can answer this most definitely, though, because we went through and talked about the experimental design. And since we know that B had the least positive charges, would you expect it to be closer to the anode or the cathode? Since B had the least positive charges, would you expect it to be closer to the anode or the cathode? Nice, Neva. Everyone's saying it. You got to list everyone. It's close. You got it. It'll be closer to the anode. So basically, the thing with the most positive charges is going to move towards the cathode that has a negative charge the most. So E needs to be closest to the cathode, and B needs to be closest to the anode. This is such a common theme, and these are some of the most challenging questions where it gives you multiple different diagrams, and you have to relate this diagram to how it relates to the other diagrams using experimental design to figure out what the heck it means. But even if we didn't know exactly, get in the habit of eliminating 2 of them and then choosing between with what's left over. That's great test day practice, regardless if you get the right answer or not. It's doing the right thing and doing the right practice. All right, last question for here in the very last bit. We'll kind of knock out a couple common theme question types. So we've got an arteriole being almost completely blocked by a blood clot. What will the velocity be the greatest? Why don't you guys tell me the formula here? Because this is a very common formula to solve for this. You got the continuity equation. Emily Kalin's saying the same thing. So it's fluid dynamics. It's the continuity equation. So cross-sectional area times velocity 1 equals cross-sectional area times velocity 2. It's the same reason that if you want to spray someone with a hose in the middle of the summer, you have to put your thumb over the end of it so the water sprays out at a higher velocity due to that decrease in cross-sectional area. So you find basically the most narrow section, which of course means that it is going to be answer choice B. Decrease area, increase velocity. Choice B is the best one right there. Pretty straightforward equation there. We will relate back to this again for a later question, but it's just a really high yield equation, so we wanted to kind of toss it in to this review just to make sure you guys were all very comfortable with your continuity. That's, of course, assuming, as it says, ideal laminar flow. That's how you know that it's going to be continuity. All right, if you have any questions on that, hit us up in the Q&A. Other than that, for the next 15 minutes, we'll go through the last learning goal, which is primarily just doing process of elimination using repetitive structures. So this actually moves a little bit more quickly, and it's really good practice just to get to notice these kinds of things. All right, so first things first, everything in this learning goal, we're going to first identify the repetitive structure. So what's your repetitive structure here? You got it. First, increase, decrease in terms of the question stems, and then also notice we also have some repetitive structure in terms of triacylglycerol synthesis or enzymatic breakdown. So basically synthesis or breakdown of your triacylglycerols. So this one, actually, we can pretty much answer just using background knowledge. What would be true of a cell if we have a lot of AMP? So tell me about like what it would be like to be in a cell with tons of AMP. Starving, Emily, exactly. So you totally, but exactly. You can, I think it's called adenylase kinase. You can actually take two ADPs and combine them together, get an ATP for energy, be left with AMP. And so we actually use AMP as a lot of your different regulatory, I guess, molecules, you could say, for a bunch of different systems in metabolism. But so yeah, if you got a lot of AMP, the cell is in trouble. It doesn't have energy. It's in dire need. And so if the cell is starving, what answer choices are you definitely going to eliminate right off the bat? This is just background knowledge without even using the passage. And we will use the passage because, yes, it says based on information in the passage, but we can use outside to at least eliminate a couple. We'll let a bunch of people answer. Yeah, Caitlin, that's what I'm thinking. Get rid of making things, right? We want to be utilizing energy, not storing more energy. So I would definitely get rid of B, because if you increase the rate of triacylglycerol synthesis, what do we use triacylglycerols for? Storage. That's fat, right? Basically, that's the storage of energy. You're not going to store more energy if you're starving. You're going to be breaking stuff down. What other one can we eliminate because of that? For the same reason. C, you got it. So get rid of B, get rid of C. That's using just your background knowledge. Now, both A and D basically show an increase in energy, not storage at least, or more consumption. In order to answer, let's look at the passage because it is a detail-based question, so we want to be careful. Looking at the actual passage itself, it said, looks like we're primarily talking about what here in the passage, since, of course, synthesis, you got it. Since it says synthesis in paragraph 1, synthetase in paragraph 2, it's probably going to be answer choice A. Without even reading the paragraph, since the paragraph addresses synthesis, since the question says based on the passage, you can basically just fall back on A and know that it's going to be correct. Specifically speaking, you can use, of course, this reaction right here. As you increase the concentration of products, what does that do just across the board, the Chatelier's principle? If you ever increase the concentration of products, what does that do to reactions? It's probably the highest yield of everything here. Shifts it left, Emily, exactly true. You got it. So it's just going to shift that reaction towards the left. Thus, of course, we're no longer going to be, of course, turning fatty acids into triacylglycerols. We're instead going to leave them as free fatty acids so we can break them down and use them. And we do, of course, have a bunch of classes on metabolism. If you haven't gone to them yet, check them out. I'm actually teaching Metabolism 2 on Thursday, 2 days from now. So that's all electron transport chain and that kind of stuff. It's a pretty cool class. I like it because it doesn't just say memorize a bunch of crap. It's more about big picture. It's a pretty good one. All right. Moving on to some other stuff, repetitive structure. What do you notice here in terms of repetitive structure? Two main ideas. So either glycerol or phosphatidic acid, exactly true. And then the other idea that's being repetitive here is something about, there we go, intermolecular forces versus surface area. Perfect. So we're relating the two to either intermolecular forces or surface area. Now, here's the question I have for you first and foremost. Excuse me. What is a bigger factor in terms of surface tension, intermolecular forces or surface area? Yeah, Charmaine, Marlo, you guys are totally right. We're talking about intermolecular forces here. Good work. And so you got it. So intermolecular forces, of course, are the main thing. Now, the thing is, you need to know glycerol, like phosphatidic acid, so we know it's carboxylic acid. Glycerol is super common, though. You need to know this thing for test day. So what is glycerol specifically? You got it. It is tri-alcohol. It's a triol. There we go. That's the proper word, Emily. So it's a triol. So now if we compare a carboxylic acid versus a triol, which one would have greater intermolecular forces, which we know, of course, it's going to be either A or B because we knew it's about intermolecular forces. You can get rid of C and D without even reading them. You got it. Glycerol. That is a ton of hydrogen bonding. If you've got 3 OH groups, oh my gosh. Yes, carboxylic acid is also hydrogen bond, and yes, they're also polar, but you're not going to beat something like glycerol. It's really good intermolecular forces there, just because you got the 3 different OH groups, so loads of hydrogen bonding going on. So notice what we're doing here, and the point of this whole learning goal, we're not even reading every answer choice. We're reading the themes, finding out what we're talking about, identifying what matters most, and then just picking the one that matches the prediction without even reading every single little bit. Saves us a bunch of time. All right, same thing for number 5. What's our repetitive structure here? Two things. First, either conduction, either good or poor. Last one is, you got it, either speed up or slow down. Perfect. So let's not even read them carefully. Let's think about the question stem here. We're talking about myelin, right? So such compounds are incorporated. So we're talking about myelin in general. What does myelin do, first and foremost? Yeah, two things. It depends what we know. I think across the board, we're like, it speeds up conduction. So no matter what, get rid of C and D because it speeds it up. And the reason that it speeds it up is exactly as Marlo and Emily saying there, is because it's an insulator. And so if we know that it's a good insulator, does that mean it's a good conductor or a poor conductor? You got it, it's a poor conductor. So even if you weren't sure about the insulating aspect of it, the fact that we know it speeds up potential or action potentials, you can get rid of C and D and once again choose between A and B. And that's why we really like all these, the repetitive structure questions, because even if you don't know the exact answer, does not matter, you can still answer the vast majority of them through just doing a little bit of strategic elimination. All right, a couple more. Same thing here. So Venturi effect, partially blocking one ureter. All right, so we're relating, well, let's do the questions then first. What are the repetitive structure here? Relating two things. Actually, the question stem actually gives you the same thing. Velocity, of course, as well as hydrostatic pressure. So this one's actually pretty straightforward because it's also addressed in the question stem itself, so that one's not too bad. All right, so let's think about this. If we're partially blocking a ureter, which of these do we know for sure? What might be the easier one to address, first and foremost? Velocity or hydrostatic pressure? I just say, just since we talked about it previously, I'd go with velocity first, because we already talked about the continuity equation, right? So we already said that, continuity equation, if you block a ureter, what's that going to do to the cross-sectional area, first and foremost? It's going to reduce it. And same thing as before, if you reduce that cross-sectional area, then of course it's going to cause velocity to go up. So we got a drop in cross-sectional area, we get an increase in velocity. So that actually lets us eliminate a couple answer choices right off the bat if we are not too sure about the other step. Get rid of A because it says velocity decreases, and then D as well. Yeah, D there, thanks, Cora. Yeah, so A and D you can knock out just using your continuity equation. So now, how do we relate this to pressure? And I kind of already accidentally gave you guys the hint. But how does this relate to pressure? And we can do some cool examples here. I might have said the word. Yeah, it's Bernoulli's equation. So the cool thing about Bernoulli's equation is this actually is the neat thing. It's a modification of the conservation of energy equation. If you were to multiply every single term by volume, notice that if you have density, actually, what do you get when you have density? Sorry, yeah, density times volume. Do you guys know what you get when you have density times volume? Mass, exactly. So notice what it's really doing. If you were to multiply everything by volume, you would left with work, because notice volume times change in pressure times volume, right? That is equal to, of course, work, potential energy, and kinetic energy. That would be your KE, and that would be your PE. So it's a derivation of the conservation of energy equation. All right, so now with that stated, the way that we often see Bernoulli show up is exactly what happened here. we had a increase in velocity, and so if you have an increased velocity, what happens to your pressure? Nice, David. Goes down, it drops, which is why it is, in fact, answer choice B. Now, the cool way that you actually see this is, does anyone live in like Oklahoma or Illinois, anywhere with Tornado Alley, where there's lots of tornadoes in the summer? I grew up in the plains. I know what it's like with all those tornadoes. There you go, Kansas, even more so, Caitlin. Perfect. And so the whole idea is, when a tornado's coming, the problem is that the wind outside your house all of a sudden gets very, 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 very fast. And so if you have a very, very high velocity wind outside the house, you have very low velocity wind inside the house. That creates what kind of pressure inside the house? Super high pressure inside, and all of a sudden, bam, the roof just pops right off. And that's actually what happens. Either the roof pops off, which is worst case scenario, or the windows actually explode out into the yard, because glass is easier to break than, shingles and all that kind of stuff. But so the thing is, how would you prevent that? Yeah, you're welcome, Cam. Draw a little picture. But how would you prevent that from happening? How do you stop your house from basically having the windows explode or the roof pop off? Bingo, Emily, just crack the windows. So if you crack the windows, it lets the air pressurize, so you don't have to worry about it. If you're in the house, you put yourself under a bathtub or something, but mainly crack the windows before you do, so you don't have to worry about cleaning up a bunch of glass. All right, a couple more things to talk about before we get out of here. We're basically just kind of picking and choosing through these questions to have some fun with it. Oxygen atom. Looking at the answers, it says either paramagnetic, that's horrible, Kaylin, or diamagnetic. What is the difference here? So what do we know about paramagnetic elements versus diamagnetic? You got it. Which one? Well, not so much lone pairs as paired electrons. You got to pair it. There we go, Emily. So para has unpaired electrons, whereas diamagnetic does not. So you'd say even or has like even paired electrons. Nice work. So now oxygen. Does oxygen have paired or unpaired electrons? If you want, you could do like your full designation. Does it have any unpaired? It does, because how many valence electrons does oxygen have? This would be your 2s. This would be your 2p orbitals, to get real specific here. It has 6, so we got 1, 2 in the s, and then 1, 2, 3, that's 5, and then finally 6. Oh man, looks like it actually has 2 different unpaired electrons, so it is in fact a paramagnetic element. Cool. So do know that about paramagnetic and diamagnetic. What's ferromagnetic? Ferromagnetic. Do you guys remember that one too? Cool. We'll just do one more after this. Yeah, I guess the main thing, it's like iron, like ferro, ferrous. Mostly just know that it's a permanent magnet. For the MCAT, you got it. They all basically go in the same direction. It's kind of the key. But you can actually, it's a permanent magnet would be ferromagnetic. Paramagnetic and diamagnetic are the ones we test in the context of actually electron spin. But yeah, an actual magnet is that. All right, so this will be our last question for the day. We're going to skip the last one because it's very passage-based and we don't have the passage clip for you. So we'll make this one the final one. But this brings up a couple big things. So it makes a cyclic lactone. How in the world would these things make cyclic lactones? And also, in terms of repetitive structure, this one's pretty straightforward, more or less stable, and relating the two. But what the heck? How do you get a lactone? What's it really do, though? So 1, 2, 3, 4, 5. 1, 2, 3, 4. I'll draw the bottom one first. Yeah, it's a cyclic ester, Emily, and the way that we get it, of course, is through an intramolecular ring closure. So the oxygen basically loops around and attacks your carboxylic acid there, pushing your electrons up, which of course gives you a ring. And I like what Marlo's bringing up there. Notice the main difference is we've got a 1, 2, 3, 4, 5, and then with the hydroxide going in and making the last member of the ring there, 6-membered ring on the bottom. Whereas the top one has a 1, 2, 3, 4-membered ring. What do we know about 4-membered rings? super unstable, lots of strain. They're pretty pissed off. They're not very happy to exist in the first place. Exactly true. And so that's why, of course, the one that's more stable will definitely be substance Y. And so you got two close neighbors. And so the largest equilibrium constant basically means that we're going to go the most forward. So it's definitely going to be reaction 2 that we have right there. So you can get rid of answer choice A, you can get rid of answer choice C. And it's, of course, because Y is going to be more stable than X, which is why it is answer choice B. Cool. All right, so know your lactones. What do you call it if instead of an OH here, you made this into maybe a nitrogen? Ooh, that'd be a fun one. Nice, David. That would be a lactam. So notice lactone, when you have an oxygen forming an ester, this would be a lactam. So a lactam would be a cyclic what then? If you have that nitrogen doing the same thing going and attacking. Nice teamwork, Emily. That would be a cyclic amide or amide. People pronounce it differently, but nice work. Cool. All right, so know your lactones, know your lactams, know your stability, and definitely know your ring structure. As I said, we're skipping the last question because we needed the passage for it, and I don't have it on the screen, so we'll call it quits. We're at time anyways. So cool thing we did today, of course, not just going through the test, we want to use it as an example to talk about those things. So with those questions with repetitive structure, even if you don't know the right answer, so often you can eliminate a bunch of them, choose what's left over, and as you know, you're going to see tons of graph interpretation on test day. You're very welcome. I'm going to be doing the next one, so I'll be doing Psych Soc next. After that, we'll basically move on to the next channel classes. But have a good short break. We'll see you guys soon.